Welcome to our first online video. Today we're doing section 10.5, and I want you to keep in mind throughout all of these videos, if I'm going too fast or too slow, you can go to settings in YouTube and adjust the playback speed to make me talk faster or slower. All right, let's get started. We're going to do a review of the last section. I'm going to determine if this series converges using both limit comparison and direct comparison. So first of all, if we just take a look at what this series looks like, it looks like the square root of n on top and n on the bottom. So it looks like 1 over n to the 1/2, which diverges. So if we use direct comparison, we want to show that the terms are greater than terms from a divergent series. So if I just remove the 1 from the denominator, then I have a true statement, and that's equal to 1 over root n. Notice there's no summation sign here. When you use direct comparison, you just compare the terms. Now, these are the terms that come from a divergent series. So our series diverges by direct comparison with the P series, the sum, n equal, in this case it's 2 to infinity, of 1 over n to the 1/2. That's a P series. All right, if we do limit comparison, we're going to come to the same conclusion, but we're going to do limit comparison with the series, again, 1 over n to the 1/2. So we take L, which is the limit as n goes to infinity of our terms, root n over n minus 1, times the reciprocal of the terms we're comparing it with, n to the 1/2 over 1. That's the limit as n goes to infinity of n over n minus 1. Now that's infinity over infinity. So I'm going to divide top and bottom by n. 1 over 1 minus 1 over n, which is 1, which is not 0, and it's not infinity. So my conclusion is the series diverges by limit comparison with a divergent series. As long as L is not 1 or infinity, your series will do whatever the series you compared it with does. All right, so let's do some basic simplifications that we'll need for this section. Simplifying factorials. If you're not certain what to do, just write out some terms. The top is 2n plus 2, then 2n plus 1, then the next integer down is 2n, and then so on and so forth. And the denominator starts with 2n and then goes down from there. So everything on the bottom is going to cancel with everything on the top except for 2n plus 2 times 2n plus 1. Okay, next one. The top is n minus 1, n minus 2, dot, 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 down to 1. The bottom is n plus 1. Next integer down is n. Next integer down is n minus 1. So now we're starting to agree with the terms on the top. So what's left is a 1 over n plus 1 times n. All right, we're going to have to do a lot of simplifying of absolute values in here. And so just want to remind you of the rules of absolute value over here on the right. If you have absolute value of a fraction, that's the absolute value of the top minus, divided by the absolute value of the bottom. And so if we're trying to simplify this, we can think of it as an absolute value on the top and an absolute value on the bottom. Now the top is simply going to be plus or minus n plus 1. in absolute value, because negative 1 to the n plus 1 is plus or minus 1. Same thing with the bottom, we've got plus or minus n. But the absolute value of plus or minus n plus 1 is n plus 1, and the absolute value of plus or minus n is n. So essentially what happens is all the minuses just go away. So if we've got negative 1 to the 2n plus 1 over negative 1 to the n, and we've got some goats here, we can pretty much just remove the absolute value, goats are positive, get rid of the negative ones, and this is a goat to the n plus 1 over a goat to the n. Sorry, my goat drawing isn't so good. And so we just get, in this case, a goat. All right, so for some of the tests, we're going to have to take the absolute value of the terms. And so the way you do that is you just take the absolute value of the terms. For example, if we have this series, which is alternating, it goes plus, minus, plus, minus, plus. If we wanted the series of the absolute value of the terms, we would just make all the terms positive. We get all pluses. Okay, absolute value, absolute convergence test. A series, these are definitions. A series converges absolutely, which for shorthand, I'll go CA, or sometimes I'll go AC, converges absolutely, if the series of absolute value converges. So that makes good sense. A series converges conditionally if it converges, but its absolute value does not converge. So that's a little confusing, but we're going to spend a whole section on this next time. The absolute convergence test tells us that absolute convergence trumps all. If a series converges absolutely, then it converges with the minuses there. So that's a very strong test. And here's an example of how you would use it. Here we have a series that looks like a p-series, but we couldn't use the p-test because the p-test is for series with positive terms. This one has minus terms in it. Again, we couldn't use limit comparison or direct comparison because those are for series with positive terms. So we have no test right now for a series that looks like this. However, if we look at the series of absolute values, we simply get the sum n equal 1 to infinity of 1 over n squared. Now that's a convergent p-series, converges by p-test. And so that means that this guy converges, since it converges absolutely. Again, we'll do some more of that next time. Okay, ratio test. The ratio we're going to form is the limit, we're going to let rho equal the limit as n goes to infinity of the absolute value of the nth term, n plus 1th term divided by the nth term. So we find that limit. If it's less than 1, the series converges absolutely, and so you can say it converges. If it's greater than 1, the series diverges. If rho equals 1, you have to find another test because there's no conclusion. Even if all the terms are positive, when you show your work, I want you to put the absolute value on the first step, and you can take it off on the second step. So here's an example. We're going to use the ratio test on these examples. I want the limit as n goes to infinity of the absolute value of an plus 1 over an. Now the step in blue here is the mental step. You don't have to show it. When you divide fractions, you multiply by the reciprocal. So it's quicker just to jump to this step. I take this is an plus 1, and then instead of dividing by an, I multiply by the reciprocal, 1 over an. All right, then, let me erase all this. I'm going to get rid of the absolute value. Everything's positive, so I don't need it. And then I'm going to group like terms. I've got 3 to the n plus 1 and 3 to the n. So I put the 3 to the n plus 1 over 3 to the n, so I can simplify easily. And I've got n squared over n plus 1 squared. Okay, limit n goes to infinity of 3 times, what I'm going to get is infinity over infinity. So I could FOIL out the bottom and then divide top and bottom by n squared, but there's a better trick, because if that weren't a square, if that were a cube, that would take a while to multiply out. So here's the trick. Just write it as one fraction squared. Now we still have infinity over infinity, but now we can divide inside the parentheses by n. So this is the limit as n goes to infinity of 3, 1 plus 1 over n. I divided every term in the parentheses by n. Now when I take the limit, I get 3 times 1 squared, which is 3. 3 is bigger than 1. So my conclusion is the series diverges by the ratio test with rho equal 3. Okay, here's another example. To speed things up, I've done the first step for us, because this is a video and you're having to watch this. All right, so there's the first step. And this is equal to, I'm going to get rid of the absolute value. Limit as n goes to infinity. Negative 3 to the n plus 1 is either plus or minus 3 to the n plus 1. So I can get rid of the minus and just put 3 to the n plus 1. All right, and then I'm going to group that with its like term downstairs, 3 to the n. Then I'm going to group the n cubed over the n plus 1 cubed. And then I've got the 2's. So I've got a 2 to the n over 2 to the n plus 1. All right, simplify. Limit n goes to infinity. 3 to the n plus 1 over 3 to the n is 3. I'm going to write the next fraction as n over n plus 1 all cubed, using the trick I did before, and then 1/2. This is multiplication. So this is limit. Again, I have infinity over infinity in that fraction, so I need to divide. Limit as n goes to infinity of 3/2. And then in the fraction, 1 over 1 plus 1 over n cubed. 3/2. 3/2 is bigger than 1, diverges with rho equal 3/2. All right, next example. A lot of factorials here. So what I've done is I've done the first 2 steps and I've color-coded things so you can see what I'm grouping. This is the n plus 1th term, and I'm multiplying by the reciprocal of the nth term. 2 to the n plus 1 over 2 to the n, the guys in black, that simplifies to 2. Then I'm going to group the terms in blue, n plus 1 factorial over n factorial, and the terms in green are the same, and then I'm going to group the terms in red. So now I'm ready to simplify before I take the limit. N goes to infinity. 2. N plus 1 factorial over n factorial is n plus 1. And so I get 2 of those. And then 2n factorial over 2n plus 2 factorial is 1 over 2n plus 2, 2n plus 1. Think of this as a fraction over 1. So limit as n goes to infinity. If I pull a 2 out of this guy, I can do some cancellation. So on top, I've got 2, n plus 1, n plus 1. And on the bottom, I've got 2, n plus 1, 2n plus 1. So kill, 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 kill. And I have the limit as n goes to infinity of n plus 1 over 2n plus 1. So this is what's left. I'm going to divide top and bottom by n. 1 plus 1 over n over 2 plus 1 over n. And that gives me 1/2, which is less than 1. So now I've got a convergent series because rho is less than 1. Okay, here's a practice problem. I suggest you pause the video, do it out, and then read the solution at the end of the notes. And we're going to move on to the root test, which is very similar to the ratio test, except rho is a little bit different. Rho is the nth root of the absolute value of the nth term, but the conclusions are the same. Rho less than 1 is the desirable value to get absolute convergence. All right, so here's an example where rho equals 1, which is case C. Let's do limit n goes to infinity. I want the absolute value of the nth term. Whoops, it's n minus 1. And I'm going to raise that. I'm going to take the nth root of that. And instead of using radicals, which I find a little bit clunky, I'm going to use a fractional exponent. Now, the stuff inside the absolute value is positive. Remember, n is starting at 1, so I can just remove the absolute value and simplify the exponents. When I have an exponent to an exponent, I multiply the exponents. So this just gives me limit as n goes to infinity of n minus 1 over n. Okay, let's rewrite that as 1 minus 1 over n. Just separate out the two fractions. And when we take the limit, we get 1. So no conclusion. That was the root test. All right, so somehow we have to show the series diverges another way. It's not a geometric series. It's not a telescoping series. So what we're going to do is use the DT, divergence test. We're going to see that the limit as n goes to infinity of the nth term, an, is not 0. And to see that, separate out what's in the parentheses as 1 minus 1 over n to the n. This is theorem 5. This is the limit as n goes to infinity of 1 plus negative 1 over n to the n, which is e to the negative 1. That's one of those limits in theorem 5, section 10.1, that you're allowed to use for free. The point is that e to the negative 1 is not 0. So the series diverges by the dt. Okay, so a couple more examples, and then I've got a practice problem for you to do. So here we go. We're going to use the root test. Rho is the limit as n goes to infinity, absolute value of the nth term to the 1 over n. Now, take the absolute value of the top and the bottom of that fraction, and the minus goes away. So this is the limit as n goes to infinity of n to the 1 over n over ln to the n over 2 times 1 over n. So multiply the exponents there, and we get 1/2. Okay. The limit as n goes to infinity of n to the 1 over n is indeterminate. It's infinity to the 0. But this is theorem 5 again. We know that limit is 1. And then ln, square root of ln, that's just going to go to infinity. So we get 0. 0 is less than 1, so our series converges by the root test with rho equals 0. Okay, last one. row is limit. You might want to pause this and do it on your own and then see how well you did, and then come back. Limit as n goes to infinity of absolute value n to the n over 2 to the, I'm going to simplify that, 2n, just multiply the exponents, which is the same as 4 to the n, right? Right. So this is limit as n goes to infinity. Ditch the absolute value, everything's positive. We get n on top because we multiply the exponents. And then on the bottom, again, multiply the exponents and you just get 2 squared, which is 4. So if we take the limit as n goes to infinity of n over 4, we get infinity, which is definitely bigger than 1. So we've got divergence. All right, so the root and ratio tests are great. I'd say, given my, choice, I would 9 times out of 10, I'm going to pick the ratio test. It comes in really handy, is much more versatile, and it's great whenever you have factorials. The reason why, let me try and find an example here. The reason why is factorials cancel so well when you're doing fractions. So if you see factorials, you should probably be thinking ratio. All right, so that's the end of this lecture. I hope it wasn't too long. I have no thing here that tells me how long I've been going. Here's some hodgepodge problems of using all different types of tests, and do those at your leisure, and the solutions are at the end. So I will see you for the next